Thanks so much, Jens, for the kind introduction, and thank you to the organizers, and thanks to all of you for coming here. I mean, at a time like this, when we have a pandemic killing hundreds of thousands of people, a worldwide economic depression on top of it, and now on top of that, also rioting across the U.S. People, seriously talking about is there going to be a civil war in the U.S.? I mean, I can, at such a time, I can think of nothing more important to talk about than the interpretation of quantum mechanics. Certainly nothing that I would rather think about. Okay, so, you all know the measurement problem, which, in some sense goes back to Schrödinger writing down the Schrödinger equation in 1926. And I think that the measurement problem of quantum mechanics could be phrased very, very simply as when does the buck stop, right? If we consider a quantum system evolving unitarily by the Schrödinger equation, it could be the state of some atoms that we're measuring, but then ultimately is also the state of our measuring apparatus, of our bodies, of our brains, of the earth, of the entire universe. When do we ever get to say that now a measurement has happened? Now, some operator has been applied, a definite outcome has been randomly chosen according to the Born rule, right? When do we get to do that? And how do we reconcile that step with the sort of unitary nature of the microscopic laws of physics? Okay, now we are all here in some sense because of a much more recent problem about quantum mechanics, which one could call just the quantum complexity problem. I'll date it to Bernstein and Vazirani defining quantum polynomial time in 1993, although there are certainly antecedents of this question earlier than that. And this question is simply, among all of the possible quantum mechanical operations that you could do on, let's say, n qubits on a system of n entangled bits, which of those operations can be implemented using a small number of elementary operations, meaning, let's say, operations that act on only one or two of the qubits at a time, exactly as Rob Myers was talking about in his nice talk a few hours ago. Okay, so in theoretical computer science, we like to identify efficient or sort of few gates with a number that scales only polynomially with n, polynomially with the number of qubits, whereas inefficient we would tend to think of as scaling exponentially, like 2 to the number of qubits. That is far from the only possible line that you could draw. And in fact, in this talk, we'll also be interested in other places to draw the line. Okay, but in general, we would like to know for those, let's say, operations that we actually care about doing, whether that means quantum computations to solve interesting problems, whether that means doing interesting measurements on quantum states, or doing interesting unitaries like that which would decode the Hawking radiation coming out of a black hole, or something of that kind. We'd like to know which of those operations can be done efficiently with a sort of reasonably growing number of operations. And so one thing we know is that this will be only a tiny subset of all of the physically possible operations. We know that just by a counting argument. To specify a general operation on n qubits will take an exponential in n number of parameters. So only there's only a tiny island of efficiency, in this ocean of complexity. But how much of what we actually care about is on that island? Okay, and similar questions have been asked for decades now in the classical theory of computation, most famously the P versus NP problem, and we know that those questions are enormously hard. Let's say most of them beyond the present ability of mathematics to answer unconditionally. So we should expect the quantum questions to be similarly hard. In this talk, I'll actually be able to show you unconditional results about quantum complexity. That's kind of the exception rather than the rule, and we'll see why that arises. Okay, but now what today's talk is about, in some sense, is are these two questions related to each other? Does the quantum complexity problem have anything to do with the measurement problem? One's first guess might be no, but I at least want to explore what would a case look like that they were related to each other. Okay, so okay, so I because of my blog that Jens mentioned and so forth, I get asked often enough, what is my preferred interpretation of quantum mechanics? And I hem and haw and try to avoid answering that, as maybe many of us do. Raphael Busso once very memorably asked me a different question. He asked, which interpretation of quantum mechanics does he believe in? So the point being that sort of he had paid so little attention to this debate that he had so could make so little sense of what all the different philosophical arguments were trying to say. He wanted me to, he said, I'll just tell you what I believe and you tell me what interpretation is that. So for anyone who might be in a similar situation, and even if you get nothing else out of this talk, what I can do is in just one slide, I can forever resolve your confusion about which interpretation of quantum mechanics is the right one for you, using a handy dandy decision tree. Okay, so here's how it works. It's very, very simple. All right, we just have to answer a few questions. First question, just is quantum mechanics empirically valid in the first place at arbitrary scales? Right, we certainly it survived every experimental test for a century, but no one has built a scalable quantum computer. We just had the first achievement, or the first apparent achievement of quantum computational supremacy, meaning any programmable quantum computation outperforming what a classical computer could do just this past fall, and at the end of what I think of as the before times. Okay, just right before the pandemic, we had the announcement of quantum supremacy. Okay, but we don't know that was with 53 qubits. Can you build a quantum computer with 1 million qubits? Will quantum mechanics still be valid at that scale? Will it, could you, with sufficient technology, actually put a cat into superposition and observe the interference fringes, right? These are ultimately empirical questions, right? My guess would be that quantum mechanics will work at any scale where we can do the experiment, but I don't regard that as obvious. So if one believes that the answer is no, then the door is open to all sorts of say resolutions of the measurement problem that are not interpretations of quantum mechanics, but are rather rival physical theories. Okay, make different predictions. Most famously, the GRW dynamical collapse proposal. It's like something that's big enough, will sort of dynamically decohere, almost with certainty. Roger Penrose's ideas, which have a similar flavor, bring general relativity into it in some way. Okay, but now on the other branch, let's suppose that quantum mechanics is perfectly valid at all scales. Okay, so maybe it is maybe the first example we've seen in physics of a perfectly valid theory. Okay, and one that will not be superseded by anything else. Well, then the next question that you have to answer is, well, what is actually the goal of physics? What is the output of physics supposed to be, right? And now we come to sort of a famous divide. Some people would say, I mean, Bohr and Heisenberg famously took this incredibly radical view on this question. They said quantum mechanics is teaching us that we should only be talking about the experiences of observers. Okay, we should be, quantum mechanics is a toolkit to be used by a person to make predictions about a system external to them. And well, what about the person themselves? Aren't they governed by quantum mechanics? Well, yeah, maybe from the standpoint of a different person. A different person could treat you as a quantum mechanical system, but you don't get to treat yourself as one. Okay, and what would happen if I get placed in a superposition state? Well, you're just not supposed to ask that kind of question, right? So the modern incarnation of these views would be QBism or quantum Bayesianism. I don't want to oversimplify it. The quantum Bayesians would vehemently deny that they are solipsists, but it always feels a little bit solipsistic to me. Because ultimately you're saying, we don't get to talk about the state of the world. We only get to talk about, the predictions that we're going to make. Okay, but all right, suppose on the other hand that we want to insist on a realist point of view. The goal of physics is to describe a state of the universe. That state was there before we were. It was there billions of years ago. In fact, we, the observers, are just some slime that, arose on, the surface of one planet, as a tiny little part of that state. Okay, so this would be the realist view. And then the last question is, well, now, without changing the formalism of quantum mechanics, do we get to add anything to it? So do we get to add, let's say, one more mathematical ingredient to it in order to pick out one measurement outcome as the real one and say all of the others are just unrealized hypotheticals? Do we get to add, for example, some non-local hidden variable that is going to govern sort of which branch, is the one that is realized, presumably with probability governed by the Born rule? Okay, if you say that that's okay, then the door is open to lots of options, most famously the de Broglie-Bohm hidden variable theory, which works just fine by construction, reproduces all of the usual predictions of quantum mechanics. But the problem is not coming up with such theories. The problem is more of an embarrassment of riches, that there are many inequivalent such theories, and it seems like there's no possible empirical way to decide among them. Okay, so if you take a more bare bones point of view and you say quantum mechanics is exactly valid, it describes an objective state of the whole universe, and we do not get to add any extra ingredient to the mathematical formalism, then I would say at that point you are inevitably led to the idea that the state of the world is a quantum state. We are part of it, and we are just on one branch, and there are other branches with other versions of us. That is the Everett point of view, the many worlds one. And you can invent all sorts of circumlocutions around that, but if you're on this branch, then I would say that what you believe is basically isomorphic to what Everett was saying in 1957. Okay, so that was my one slide decision tree. But now, I want to address a meta question. Sort of, does any of this matter?
Scott, sorry to interrupt, but this may be a good moment to brief interrupt. There's been a question by the audience in the chat on whether the scale is spatial only in your interpretation decision tree. So is this because the time seems to be special in Copenhagen and Cubism? Or maybe
I didn't understand the question.
Yeah, maybe the speaker asked the question himself. Can you maybe unmute yourself and ask the question? Yukata?
Yeah. So sorry that this is now is a network trouble. It's
Sorry, who is this? Who is asking?
I mean, so Yutaka is asking.
Oh, hi, yeah.
Hi.
Well, what's the question?
This is that your skill in the previous slide.
Yes.
In that it seems to be that the consider on the spatial scale only. This is because in the Copenhagen interpretation cubism in the many world in the double is the bomb interpretation.
Yeah.
It is that's the they is only that the time parameter is a special.
Time is special. I mean,
Yes.
in
the
all
special
of,
means that is the detach from that the special parameter is.
Yeah.
That's why.
Yeah. I mean,
the
okay.
special. That's the.
I mean, look, there are many things that one could say about time in all of these interpretations. I don't think that the decision tree that I showed sort of depends on those questions. In fact,
Right.
nothing that I said really depended on the detailed nature of space and time at all, right? I was just talking about spaces of states, right?
Yeah.
Now, it's true. Like if you believe in Bohmian mechanics, then you have to make particular choices. Where does my hidden variable live? Bohm said, position basis is the positions of particles in three-dimensional space. That's obviously a very specific choice. And from a modern point of view, we'd say it's an arbitrary and maybe a wrong choice. But okay, but you can, the basic idea, you can adapt to sort of whatever is your Hilbert space and, whatever you take to be your, sort of fundamental degrees of freedom. Likewise in, the Bohmian mechanics does have the issue that you have to choose a reference frame, okay? Now, that doesn't have any empirical consequences that would violate special relativity, but you do have to choose one. That's one of many features of Bohmian mechanics that some people would find unattractive. So, there's a lot to say about space and time, but I'd like to, since it's not really relevant to my talk, I'd like to just sort of go on. Okay.
Yeah.
Okay, thanks.
Yeah, thank you. Good.
Yeah, sure. So, okay, so I want to address the question when people argue about these interpretations. So, not counting the dynamical collapse interpretations, which of course do ultimately make predictions, like that, you will not be able to put large enough masses into superposition, and, and that would someday have an empirical consequence. But if we consider many worlds and Copenhagen and Bohmian mechanics, do beliefs in these things ever pay rent for anything? Are we only arguing about words, about language in some fancy way, and not about anything in the world? I mean, if you can't point to any experiment that would even in principle distinguish these interpretations, then what is even the substance of what is being argued about? Okay, so I think that's a very important question to ask. But now a usual answer that people would give if you push them about this is, well, what about these sort of extreme scenarios that we're all familiar with, like Schrödinger's cat or like Wigner's friend, right? I mean, surely, like, if I put a cat in a, equal superposition of alive plus dead over square root of 2, like physics ought to be able to tell us, is there a fact of the matter about, okay, what is it like to be that cat? Is it not like anything? Is it like two different experiences where, one of, or, is it like, one of a cat that gets killed and one of a cat that doesn't get killed? So sort of, at that point, it becomes untenable to, insist on this distinction as Bohr wanted to between a micro world and a macro world, right? Because now quantum mechanics has sort of invaded the macro world, by assumption. And it seems like we have to stick our necks out at some point and make some statement about what we think is really happening there. And by the way, I mean, for me, personally, the number one reason why I got into quantum computing and information in the first place, is not because of any of the applications. I mean, there are some. A lot of them have been, unfortunately, massively overhyped and oversold. But for me, the number one application of a quantum computer has always been to just prove that it works at all, right? Disprove the people who say that this is impossible, right? Show that quantum mechanics can actually, work at this scale of something as complex as a computer. Okay, and going even beyond a computer, we can talk about the Wigner's friend scenario, which is basically just the same as Schrödinger's cat, except that now you're the cat. Okay, it's just a person instead of a cat. Where now you imagine yourself in the position of that person. You ask about what is your experience as you're being manipulated by someone else in a coherent superposition over two different mental states. Okay, so now David Deutsch, who was, I would say along with Feynman, considered one of the founders of quantum computation, had a famous paper in the mid-'80s called Quantum Theory as a Universal Physical Theory. And in that paper, he sort of said, is it really true that, Everett's interpretation has no empirical consequences? Well, because what if we could do, what if we could take the entire state of your brain, scan it into a computer, upload your brain to a computer? That may sound fanciful. I have a lot of friends in Silicon Valley who think that, it's a matter of a decade or two before we can do that. I think that their time scale is a little on the aggressive side. Okay, but suppose we can do that. Suppose we can even load the state of your brain into a quantum computer, and then we can do a double slit experiment with, a state of you thinking one thought and a state of you thinking another thought. Well, surely then it must matter, say whether, Everett's many worlds are real or not real, right? It matters just for your experience. Now, it's true that if you were to go and publish a paper later about what it had been like to be in superposition, then any Copenhagenist could come along later and say, oh, I could have perfectly predicted what you would have said in that paper, just from Copenhagen considerations, right? And so this does nothing to prove many worlds, whatever, right? But while the experiment was ongoing, it would be like, you might have this moment of like Zen enlightenment where, you couldn't tell anyone else about it, but, you would see that, that you were in a superposition of states or something, okay? So, I don't know, but, as zany as this sounds, this was one of the thoughts that led Deutsch to the idea of quantum computing in the first place. Okay, that's the history. Okay, now, meanwhile, in the very, very different realm of quantum gravity, I hesitate to say the much more down-to-earth realm, but that's almost what it is. Our friend Lenny Susskind, so, I put a picture of him on the slide, but I'm also seeing him on video at the same time, cared about a different kind of macroscopic quantum state. So he cared about superpositions over different space-time geometries within the context of ADS-CFT, for example. So he cared about situations where you would have, in an ADS bulk, you could have different space-time geometries, like one containing a black hole, another one containing no black hole, for example. And those ADS states, those different geometries, each one will have a CFT dual, which is simply some quantum state living in some Hilbert space that lives on the boundary of the ADS. And so by the laws of quantum mechanics, we must be able to superpose two of those states, which would then give us a superposition over two different space-time geometries, like the state that I've shown there. Okay, and that led to all sorts of difficulties that people argued about for the last decade. For example, within the context of the firewall paradox, And this debate went under terms like the state dependence of observables. Okay, but basically what it was about is that, to apply quantum mechanics in the ways that we know sort of presupposes that which space-time background you're in. And, if the set of operators that you're allowed to apply to make a measurement depends on the space-time background, so it's sort of state dependent, then, this from the standpoint of conventional quantum mechanics, that kind of seems like nonsense, right? Because you, the observer, are supposed to be external to the system. Okay, but we, as Rob Myers discussed, we've learned in so many contexts that complexity, circuit complexity, could be a very helpful tool for thinking about issues in quantum gravity. And so, inspired by that, Lenny asked the question, could complexity sort of provide a principled criterion for when two branches of a quantum state are really separated for good? So when, we just have, our superposition of a black hole space-time, a no black hole space-time, when they're sufficiently far apart from each other that we might as well think about it as just two different space-time geometries, each, presenting itself to us with probability half, and where, whichever one we're in, we get to apply quantum mechanics within that one. Okay, and so in particular, a few years, it seems really hard to turn these sort of vague thoughts into any concrete, even a concrete question at all. But that's exactly what Lenny did a few years ago. And he just emailed me a question that I just had to sit up, and just, it's one of these things that I like, you think like in 10 seconds, maybe I'll be able to say, no, this is completely wrong-headed, but no, I couldn't say that. Okay, and it turns out to be right, actually. So he said, look, is it just true in general that the circuit complexity of sort of seeing interference between two different orthogonal states, let's call them V and W. These could be a state of a black hole and of no black hole, for example, that this is basically equivalent to just the complexity of mapping V to W. So in other words, he's asking, if we had the computational ability to distinguish a superposition, of V and W from a probabilistic mixture of V and W, or what's easily seen to be equivalent to that, if we had the ability to distinguish different superpositions from each other, like V plus W from V minus W, for example, then would we also necessarily have the ability to map V to W with a sort of similarly complex computation? Map W. Yeah.
So are you making, when you're talking about complexity, are you making any kind of locality assumptions? Because like
no,
like
no,
one
I'm not.
in this context, like also propagated by Zurich, but also others, is like the idea that you would call a branch in the AND/OR problem if you cannot operationally distinguish the setting anymore from a classical alternative, and you can't make an operational measurement of the superposition. And then if you have that, you can just as well talk about the branch because that's operationally indistinguishable.
Well, I mean, we are going to try to operationalize these notions. Yes.
I see.
We're going to do that. Okay, we're going to do that by talking about complexity as an abstract thing. We're going to relate the complexity of one task to the complexity of another task.
Wonderful.
And as for the details of, the details of how we define circuit complexity, the wonderful thing is that for this talk, they won't matter. Okay, so I'll sort of show you a paradigm result that can then be instantiated with pretty much whatever is your favorite definition of circuit complexity, whether it involves local gates, non-local gates, it'll work for any of that. Okay, under some very, very mild conditions.
Okay, thanks.
Okay, So what I want to say, so we have a paper which now, my postdoc Yossi Atiyah is now a co-author, and now Lenny too has agreed to be a co-author on this paper, and this should be on the archive any day now. When I promise a paper is going to be done any day, I really mean it. So you can take that to the bank. Okay. So there were two
any
theorems
day.
here.
By that you mean any day. Any day. Like
that's right. That's right. I was careful in what I said. I said any day.
Yeah, I'm still waiting. I'm still waiting for the paper that was supposed to come out in the summer of, I think, 2013.
Yeah, I know.
Never mind.
Well, yeah. Well, now, right, and now I get like an hour a day at most when my kids are not screaming. But okay, so. So there are two theorems. There are two main results here. The first theorem is given two orthogonal states. I'll just think of these as states of n qubits. And, just for vividness, I'm going to call them alive and dead. Alive cat, dead cat. But, they could also be anything else. Now, suppose that there is a quantum circuit with T gates that can distinguish two different equal superpositions, like alive plus dead from alive minus dead. By which I mean there's a circuit we can apply, and then we measure some particular qubit, and if we see a 1, then the state was alive plus dead, and if we see a 0, then it was alive minus dead. Then there is also a quantum circuit with only slightly more gates. It's going to be about 2T gates. 2T plus order n, let's say, that can swap the alive and dead states. Okay, so do a swap operation, which in particular, would mean that you could bring a dead cat back to life. Okay, you could perform quantum necromancy. Okay, which of course raises the question of, in what sense was the cat, even dead in the first place, right? I mean, if you can observe the interference, then you can actually also rotate between the states. And this result is robust in the sense that even if we only had a noisy ability to distinguish the two superpositions, that would give us a noisy ability, to map a dead cat to a live cat, or for example, with some success probability that was bounded above 0. Okay. All right. The second theorem is a converse to that, although it's a converse with a little exception to it. Okay, it says suppose that we had a quantum circuit with T gates that mapped, a dead, the dead state to the alive state with an amplitude of A. Okay, so it brings a dead cat to life with some success probability. And let's imagine that the same circuit maps the alive state to the dead state with an amplitude of B. Then there is also a quantum circuit with about the same number of gates, almost exactly the same number actually, that distinguishes a superposition of alive and dead from a mixture of alive and dead, or that distinguishes two different superpositions, like alive plus dead from alive minus dead, with a fidelity, like a success probability, equal to the absolute value of A plus B over 2. Okay, so just to give examples, if we had a perfect swapping ability, so A and B were both 1, then we would also have a perfect distinguishing ability. Okay, if we had a unitary that could map dead to alive, but maybe alive just goes to something that's orthogonal to both of them, well then the fidelity would be a half. Sorry, the fidelity being a half means that, like, the success probability at distinguishing would be 3/4. Okay, I didn't say that. Okay, and if we had an operation that mapped dead to alive, but it mapped alive to minus dead, well, now A plus B, A is 1 and B is -1, which means that A plus B equals 0, right? And so now, that's the one kind of situation where you don't get any distinguishing ability, even though you did have the ability to swap the states. Okay, so this is what the theorem says. Now, you know, once you've had the thought to, you know, even formulate these questions, you know, the proof, you know, the proofs of both directions are really just exercises in quantum information. I mean, you know, Lenny basically just used me as a homework assistant, you know, TA or something. Okay, so you know, I can show it to you, right? So all right, so suppose that we have the swapping ability, like, so suppose we can distinguish the superpositions, then how do we bring a dead cat back to life? Well, I'll show you how. All right, so let's just give names to two different superpositions. So alive plus dead over square root of 2, I'll call it psi. Alive minus dead over square root of 2, I'll call it phi. Okay, now, you know, a profound result is that by rearranging, we see that the alive state is equal to psi plus phi over square root of 2, while the dead state is equal to psi minus phi over square root of 2. Change of basis. All right, now suppose that C is our quantum circuit, and suppose that C can distinguish psi from phi. What that would mean is that on input psi, C produces like a 0 qubit tensored with some other garbage that we don't care about, whereas on input phi, C produces a 1 qubit tensored with some possibly different garbage that we again don't care about. Now, how do we use C to bring a dead cat back to life? All right, well, it's simply this. All right, we take our cat that's either alive or dead, we run it through the circuit C. Okay, now remember that alive is psi plus phi and dead is psi minus phi. So then what does applying C do? Well, it's going to take psi plus phi, and just by linearity, it's going to map it to 0 garbage plus 1 garbage. And it's going to take the dead state, psi minus phi, and it's going to map that to 0 garbage minus 1 garbage, right? Okay, and then, you know, once we're in that form, then we can easily swap between these two states just by applying a Z gate to the first qubit, you know, a phase gate, right? Flip the phase if the qubit is 1. And after that, all we have to do is invert C. Just, you know, apply C inverse, and then that takes us back to the alive and dead basis. And now if our cat was alive before, it's dead, and if it was dead, now it's alive. All right, done. You know, and then, you know, to prove the robust version of that, then you have to actually do some calculation. But, you know, but all the ideas are here. Okay, so what about the converse direction?
Can I ask
yeah.
3 questions? Actually, my question is, can you say a bit on the robust version and the overheads included and what the fine print is? I mean, without going into too much.
Yeah. Well, so I mean, the overhead you can just read off from the circuit, right? It's just twice the number of gates in the original circuit,
okay.
plus 1. Okay.
Will this also be true in the robust version?
What? The first question. Yeah. So regarding the robustness, if you have a like a fidelity, you know, if you have an error of epsilon, let's see, in distinguishing one way, let's say, and an error delta distinguishing the other way, then you're going to have a success probability of your swapping of just 1 minus epsilon minus delta. So it's very simple. Okay. Good.
There are 2 more questions I should add. I mean, maybe the people asking the question in the chat should ask these questions themselves because they seem rather elaborate.
Yeah.
So maybe,
okay. So maybe, you know, I'm almost done. So maybe we'll.
Oh yeah, then we shift these questions to the end of the talk.
Good. All right. So for the converse direction, we just suppose you have a unitary that maps dead to alive and alive to dead. Well, then, you know, there's a very simple quantum circuit that we can use to distinguish alive plus dead from alive minus dead. I just take a control qubit, I put it in the plus state, which means 0 plus 1, and then condition controlled by the control qubit being 1, I apply my unitary U that swaps alive and dead. Now, the effect of that is that if I was in the alive plus dead state, then my control qubit is unaffected. If I was in the alive minus dead state, then I pick up a phase, and now my plus control qubit has become a minus qubit. And now I just have to measure that in the Hadamard basis. Okay, and once again, I just, you know, I do the robust version of the calculation, I get that absolute value of A plus B over 2. Okay. All right. Now, a few things that I wanted to notice here. Okay. So, okay, the first one I already said that the power to distinguish the superpositions always implies the ability to bring a dead cat back to life, but the power to bring a dead cat back to life does not always imply the ability to distinguish the superpositions. There's one exception, right? If our circuit mapped, I'll say, alive to dead and dead to minus alive, then we need not get any distinguishing ability, because then A plus B equals 0. Okay, now, when you first see that, that looks like some technical defect of, the construction that we use from the proof. But with Yossi Atiyah's help, actually, we were able to show that this is inherent. Okay, this is not an artifact of the proof. There are situations where these where you can map alive, you can map like, let's say, V to W, you can map W to minus V, and you can by polynomial size circuits, but it takes an exponential size circuit to distinguish V plus W from V minus W. Okay, and we can actually prove that unconditionally. Okay, and the way that we can prove that unconditionally is simply by considering Haar random states, right? Where, like, we know that if I pick a state randomly, then with overwhelming probability, that you will need an exponential size circuit to prepare it, right? So we don't have to make, unlike the usual situation with circuit complexity, we don't have to make any unproved assumptions, not even P not equal to NP. We can just prove that that there is this exception to our result, and more generally, we can prove that our results are exactly quantitatively tight. So, like, for example, that absolute value of A plus B over 2, that is the best that you can do. Okay, that cannot be improved in that theorem, and that's an unconditional statement. And that again comes from constructions involving Haar random states, where we know that complexities of certain tasks will be exponential with overwhelming probability over the choice of the state. I'm not going to show you that. Okay, now a second point that I wanted to make is that the ability to distinguish a dead cat from a live cat does not imply the ability to map a dead cat to a live cat, and vice versa. The ability to bring a dead cat back to life does not imply the ability to distinguish a dead cat from a live cat, right? And it's easy to give examples that show this. For example, suppose that a dead cat was the all zero state. Well, suppose that a live cat was some exponentially complex state that was orthogonal to the all zero state, right? Well, in that case, it's very easy to distinguish the two states. I just measure in the 0-1 basis, and I see, if I got all zeros, the cat is dead. If I got any ones, the cat is alive. But by assumption, it is exponentially hard now to go from the dead cat to the live cat. Okay, and conversely, if I consider a state that's like the 0 state plus an orthogonal exponentially complex state, or the 0 state minus an orthogonal exponentially complex state, those states are very easy to swap with each other, to map from one to the other, but they're very hard to distinguish. And we know that they're hard to distinguish because if they were easy to distinguish, then the 0 state and the exponentially complex state would be easy to swap by the main theorems that we proved. Okay, so the general lesson here is that the ability to distinguish in one basis is related to the ability to swap in the complementary basis. Okay, not the ability to swap in the same basis. Okay, you have to make the switch from one basis to a complementary basis. And by the way, like the I and minus I basis would also work here, but it has to be two complementary bases. Okay, so implications for quantum gravity. Well, as Lenny wanted, we can treat a superposition over spacetimes as effectively decohered, so that, for example, we have different operators in each spacetime unless it's feasible to map one spacetime to the other. There's no shortcut to interfering them other than that. And unconditionally, we can say no polynomial time experiment can ever observe interference in a superposition between a state that is exponentially complex and a state that is only polynomially complex, right? Because in order to do that, you'd have to be able to map the polynomially complex state to the exponentially complex one, which, is an exponentially complex problem. Okay, and then if you combine this with our earlier result of me and Lenny about the growth of complexity in ADS-CFT, then what you get is that assuming a reasonable complexity conjecture, like that P space is not in PP/poly, or some complexity class that's not supposed to be in another one is indeed not in that other one, then what you would conclude that no polynomial time experiment can observe interference between a very, very early time CFT state and a very, very late time CFT state. Because, under that complexity hypothesis, the very late time CFT state would indeed be exponentially complex. So, these are a few of the implications that you could get. Okay, now, the foundational implications. I mean, I would say that to some extent, our result is simply formalizing the folklore that, interference between branches stops being detectable precisely when irreversibility sets in. Or in other words, when it's no longer feasible to map one branch to the other. And I think a lot of people would have told you that off the cuff, but now we can actually prove it. And, and we can even see the little case where that correspondence breaks down. Okay. Okay, so like philosophically, well, suppose someone held that, our participation in the thermodynamic arrow of time. So in other words, like irreversibility was somehow essential to our experience as observers. Well, then from that, and together with our result, it would follow that there would not be such a thing as an experience of a coherent superposition, right? If in order to be able to do an experiment that shows that an observer was in a superposition, that has to be a reversible observer, right? It cannot be an irreversible observer, okay? And so if you think that irreversibility is somehow essential to the nature of observers, then there would be no way, even in principle, to sort of experience the many worlds for yourself along the lines of Deutsch's proposal. And, arguments over the reality of the wave function could just continue forever, just like they do now, with no one having these Zen moments of enlightenment about it. Okay, so sorry if that's a downer. There are some obvious objections, that people could raise. One is in complexity theory, we like to call anything that's polynomial time efficient. But, you might say bringing a dead cat back to life, as powerful as that sounds, it's merely a linear time operation, where we mean linear in the number of atoms in the cat, right? You could say it is merely thermodynamics hard. Okay, but again, these results have the virtue that they sort of relativize to whatever notion of complexity you care about. So we could say, look, if you can, if necromancy is a thermodynamics hard problem, then observing interference is also thermodynamics hard, right? So it doesn't have to be exponentially hard. We could merely talk about Avogadro's number hard, and that would the same results would go through. Okay, second objection, you might say, aren't and like using complexity as our criterion, aren't we reifying what's merely a technological difficulty, right? Isn't it, if something is exponentially complex or even Avogadro's number complex, isn't that merely an engineering problem? How could that possibly have like philosophical or foundational importance? Well, so I don't know the answer, but just one thought that I want to throw out is that once you bring cosmology into the picture, and for example, the fact that we seem to live in a de Sitter space, sometimes what had previously been a merely technological difficulty, like for example, in recohering a superposition, takes on a much more fundamental appearance. This was a point that I took from a paper by Busso and Susskind on the multiverse interpretation of quantum mechanics, where they say, what might look like just a technological difficulty in recohering, the two branches of an observer. Well, if the information about that is actually about which branch you're in is headed toward the de Sitter horizon, then in our cosmology, that looks like it's impossible even in principle. Okay, so sometimes what might look like a technological difficulty is actually more fundamental. I don't know if that's true in this case, but I'm sorry for going over, and I'm happy to take questions at this point. Thanks for listening.
Thanks so much indeed.
Yeah.
It was a wonderfully stimulating talk. That was excellent. I mean, there were also many questions in the chat. I didn't want to interrupt you too much.
Right. Okay.
Let me do the following. Let me first maybe state a couple of more technical questions on the argument itself, and then move on to more conceptual or even philosophical questions. I mean, I might start with a technical question. When you hinted at this kind of converse using Haar random states, you said that this A plus B over 2 bound is effectively tied. You mean that if you take Haar random states, then with high probability you can arbitrarily well approximate that that probability.
What I mean is that you can't do better than that. Okay? There is a construction that uses Haar random states as a component. You have to be a little bit clever about how you use them, but you can take Haar random states, put them into a construction where it will have the property that I will have 2 orthogonal states, let's say V and W. There will be a polytime circuit that maps V to W with an amplitude of A. There will be a that same circuit will map W to V with an amplitude of B, but there will be no polynomial time circuit that can distinguish V plus W from V minus W with a fidelity exceeding absolute value of A plus B over 2 by more than an exponentially small amount.
Okay. That makes
perfect. Great. That's the statement.
Okay, thank you. Then there was a question by Maris. Maybe that's a good question to follow.
Sure. Does the irreversibility ever set in unless we wait for an exponential amount of time? I mean, I guess that depends on which kind of irreversibility we're talking about, right? If we care about merely the thermodynamics irreversibility, like I mean, in practice, we are constantly willing to say things are irreversible, like cream mixing into coffee, like someone dying, glass shattering on the floor, even though reversing that evolution is presumably not an exponentially hard problem. It is merely a thermodynamics hard problem. Okay, but in that context, we're willing to say that, well, at least relative to all the technology that we know about, it's just not going to happen, right? And the point I was trying to make is that there is the equivalences that I showed you in this talk. You can scale them to sort of whatever is your notion of of complexity, right? So if one task is exponentially hard, then so is the other task. If one task is thermodynamics hard, then so is the other task, and so forth.
Okay. Then Ed Witten ask a question.
Yes. In the particular case of Schrödinger's cat, presumably our obstruction involving the signs of A and B would not arise. Right. Well, so I find it very hard to imagine a situation where I could bring a dead cat back to life, but only via a unitary transformation that also mapped a live cat to precisely minus a dead cat. and not anything orthogonal or to dead cat, and not with any sign other than exactly -1. I don't know why that would be the case. We were able to give a construction showing that there are situations involving Haar random states where that would be the case, but I have no idea. I can't prove that would not be the situation. with the cat, but I see no reason why it would be.
Okay. Then Peter had 2 questions. Actually, maybe it's best if you post them yourself because they were a bit elaborate and complicated. Maybe you could pose your question in like actual words. Then maybe easier to answer.
Okay. Nice talk, by the way.
Thank you.
The first question was more philosophical, but the second question refers to your result.
Mm-hmm.
In your proof, you are using circuit C.
Yes.
And later you used reverse.
Uh-huh.
But the C circuit was supposed to do this discrimination.
Mm-hmm.
What if performing the discrimination itself is inherently irreversible, so the circuit C inverse doesn't exist?
I understand it's a good question, and here is the answer to it. The answer is there's a standard trick in quantum computing where you could take any irreversible quantum circuit, so any circuit that involved measurements or interaction with the environment as primitives, and you can simulate it using a reversible circuit. Okay, this is sometimes called the church of the larger Hilbert space, right? But like anytime you wanted to have a measurement in your original irreversible circuit, you can then simulate that by, let's say, a C0 operation onto some ancilla qubit that then won't be used for anything else, right? And in this way, you can, if there is an irreversible circuit that does the discrimination task, then there will also be a reversible circuit of the same complexity that does.
Okay, I was conjecturing that such a...
Thank you.
I was conjecturing that there was such a result, but you didn't mention it.
Thank you.
The other question was more philosophical about this Deutsch experiment.
Yeah.
If I upload, something is not wrong with your mic, I'm afraid.
With my mic?
Yes.
Can you hear me at all?
I only almost hear squeaking.
And now your sound is very bad suddenly. It was very good throughout the talk. Now suddenly, what a robot voice.
I had this happen before. As soon as my question or in my audio great.
Oh.
Yeah.
Good. Now let me pose the question anyway. You were describing this Deutsch experiment of uploading your brain and then looking for the experience. But don't you have to download your brain again into yourself before you can actually experience the experience?
Well, I mean, it depends on whether you think that a simulation you would have experience or not. This was exactly what I was talking about toward the end. Some people might believe that the reverse simulating experiences are ones that are added in some irreversible to the clubbing rate, right? But if you want a reversible computer, such as a quantum computer, have experience.
Scott, I think your sound is.
All right. Should I make
I'll hearing Scott in a similar fashion as I do, then it's not very very clear. I would everybody's muting the microphone.
Yeah, let me try to mute everyone. That might be, I don't know if that's the reason.
I don't think it's going to work. Let me try to log in again.
I mean, it has an entertainment value, but not much more. So, well, first of all, everybody should mute the microphone, maybe except Shira and myself. And then even maybe Scott might mute and come back.
I can actually do that. I can mute everyone by clicking, and then we just unmute ourselves. Let me try.
Yeah, please do so.
Okay, so
Hi.
I muted everyone. Yes.
Good.
Ah, very good. So I mean, okay, good. Then let's have a further question. Say by Deepak. where
Yes.
it was a technical question asking
Okay.
whether you can recapitulate how theorem 1 and 2 lead to the conclusion regarding interference of a more complex state with a less complex one.
Yeah, sure. So, all right. Well, look. I mean, suppose that we have. You know what? Should I try to do the share whiteboard thing? Can I do it? Oh, no. I'm not the host now. So
No. You can. Now you can. I made you
okay.
share.
All right. Here we go. Whiteboard. Okay. All right. So look. Is it this one?
Wonderful.
Okay.
Very good.
All right. So suppose I've got a state like this. Simple is a state of polynomial complexity. Complex is a state of exponential circuit complexity, right? So now I want to say that I cannot actually feasibly distinguish this from the state simple minus complex over square root of 2. In other words, that any circuit that could do this distinguishing, even with any non-negligible bias, with any better than chance, would have to itself be an exponentially complex circuit. Now, why do we know that that's the case? Well, we can just appeal to our theorem, right, which says that if I could distinguish the one from the other, then I must be able to map the one to the other. Then I must have a unitary U that, for example, could map simple to complex, with some, and this will have at most twice the gate complexity of my original circuit, and it will also have some non-negligible success probability. But if complex, again, was a Haar random state of 2 to the n circuit complexity, well, then by definition, such a U has to be exponentially complex.
Mm-hmm.
Would you mind if I try to repeat?
Sorry, I can't hear that.
So that it would really.
Sorry, I can't hear.
I said, would it? Can you hear me now?
Oh, now I can hear. Yeah, thank you.
Okay. No, I just wanted to repeat it myself. That maybe I could really register it. But it's a very simple argument, but also subtle argument.
Yeah.
So you have the superposition of simple plus minus complex.
Mm-hmm.
And your theorem says that if you want to distinguish between these two states, the one with the plus and the minus, then that also implies the ability to swap them. Right?
Yes.
And in order to swap them, you need an operator which can create those states in the first place.
Well, they can map one to the other.
That can map one to the other.
Yeah. They might.
That operator has.
I should say that they might both be exponentially hard to prepare. All you can conclude is that it is then easy to map one to the other. And if one of them happens to be the all-zero state, then the other one is then easy to prepare.
And then if that operator is exponentially complex, then then it is exponentially complex to distinguish superposition. All right, thank you so much.
Yeah.
Okay, wonderful. Then maybe let's have a last, because we're running a bit over time, let's have a last recorded question by Ed Witten. Maybe Ed, you could ask your question yourself, maybe in words. Maybe that's easier than reading the question.
I just want to respond slightly more to the answer you gave me before.
Yeah.
Which is that for cats, alive and dead can be distinguished by simple operators with different eigenvalues. So it seems that there's a simple circuit that would multiply alive to itself and dead to minus itself. So if you had the circuit, the problematical circuit you discussed, you could modify it to get rid of the minus sign.
Well, the issue is, the distinguish between the distinguishing circuit and the mapping circuit, right? So yes, I agree that it is very easy to distinguish alive from dead. But what I'm concerned with is distinguishing alive plus dead from alive minus dead. And by the theorem, what that is equivalent to is actually mapping dead to alive, mapping alive to dead. Now, I don't know of any general argument by which, I could take a circuit that would take the dead state and map it to the alive state, by which I would know that that circuit would not map the alive state to minus the dead state, or that if it did, it could be easily modified to avoid that. I mean, I expect that that would be the case. I just can't prove it.
Well, I'm suggesting that not for abstract states, but for cats, that it could be easily modified because there are simple operators that have different eigenvalues for dead and alive cats. And we could use that to make the circuit that modifies the one that is
okay. It might, yeah. So it might well be that in particular cases, yeah, you can use properties of your system. I mean, certainly none of these problems, involving, including the necromancy problem, bringing to life the dead cat, will have any exponential hardness, right? At worst, these problems will have like linear hardness. You just would have to arrange all of the atoms one by one. Beyond that, is there?
You gave examples in your talk showing that the minus sign could be meaningful. I was just saying that for cats, because dead and alive are distinguishable in a simple way, it wouldn't be.
I see.
Specific structure of the specific.
I see. Yeah. You may well be. Yeah. Okay. That is probably right. And so in that, let's say in that situation, maybe you can modify the circuit. And,
Maybe let's have maybe a last question, because that's an interesting question by Adam Brown to everyone. Maybe Adam, you would post the question yourself, and then that seems easier than me reading it.
I maybe just read it. I have a baby on my lap.
No.
Wow. So I shall read it. Okay, good. Sorry. Perfect. So the question is, as you alluded to at the start, if you have n qubits, then there are doubly exponentially many mutually large relative complexity states.
Yes.
So combining this with your theorem, this suggests that Hilbert space is big enough for there to be doubly exponentially many very hard to interfere branches.
Yes.
Do you agree that there can be some doubly exponentially many Everettian branches, or does something else limit their number?
That's
a good point. Yeah.
Right. Well, so now it's going to the main difficulty with that question is, in the setting where that question would be relevant in the first place, how do we even define the branch structure, right? You could say that like a branch structure is something that we can pick out maybe in a world like ours, because we are so far from the complexity maximum, right? In a world where our state looked like a Haar random state, you would have what the Everettians call the preferred basis problem, but you would really have it with a vengeance, right? I mean, like you would have all sorts of different bases in which you could decompose your state, right? Of course, if it's an orthonormal basis, then there will be merely an exponential number of states. You could choose to write your state as a superposition of a doubly exponential number of branches, but there might not. I guess you might need a good reason to do that, right? And maybe in that situation, maybe the most natural thing to say would just be that there was no longer any branch structure at all. But having said that, I completely agree with the earlier statement that we can find a doubly exponential number of pairs of states, such that their pairwise inner product is close to zero. And if I superpose those two states, then I would not be able to observe the interference in that superposition by any polynomial time experiment. And so I might as well just think of it as a mixture.
Wonderful. So I mean, that's maybe good for now. Thanks for this enormously stimulating talk and the good discussions we had